is Ian Fairweather. Ian is founder and president of Fairweather IT, LLC, an applied science and technology consulting company headquartered in Bozeman, Montana. FIT's major areas of expertise are in mining remediation and exploration. Ian has a bachelor's in geology from the University of Montana and a master's degree in geology geophysics from the University of Wyoming. His primary area of expertise is remote sensing, with expertise collecting, processing, and interpreting hyperspectral, multispectral, thermal, radar, and LiDAR data sets. Ian and the team at FIT have pioneered the use of unmanned aerial vehicles for use in mining remediation, including remote sensing surface cover type classification and remote collection of environmental samples. In partnership with Atlantic Richfield Company, FIT has invented a patent-pending technology for remotely collecting water samples from flooded mining pits and other hazardous bodies of water. So, with that being said, I will now turn you over to Ian.
Hello, everyone. Can you hear me fine through the microphone?
You sound good.
Okay, great. And is my presentation up? It looks like it is. So
yes, we can see you.
Perfect. All right. Well, this is new for me presenting via Zoom meeting, but we'll give it a try. I have a lot to present here, so we'll get started right here. So we'll be talking about sampling using UAVs for aerial sampling of water samples from flooded mining.
Hey, Ian.
Yes.
This is Susie. You're a little boomy, so could you maybe turn your speakers down just a little bit?
Okay, yeah, I'm going through a headset right now. Does this sound any better if I move the mic away?
That's fine.
Okay.
You're good.
Move the mic away from my face. A little outline of the presentation. We'll just give a brief overview of FIT. We'll discuss water sampling via UAV. We'll go over the two versions of the WaSP that we've created, the controls and how you operate and use the WaSP, safety benefits for using the UAV for water sampling, different payloads that we have tested and used, results of our water sampling at the Berkeley pit, and then some potential other uses for the WaSP. So, as was said, FIT is an applied science and technology firm. We're located in Montana. We have employees with diverse scientific and technical backgrounds. Our main areas of expertise are remote sensing, aqueous geochemistry, gas geochemistry, geophysics, information technology, unmanned aerial vehicles, and technology development of unmanned aerial vehicles, unmanned surface vehicles, underwater vehicles, and so forth, and other technologies. So but the main focus of this talk will be our water sampling platform, also known as the WaSP. So due to hazards associated with direct water sampling, one of our clients requested that we develop a technology for remotely collecting water samples and performing water column profiles from hazardous bodies of water. With this, we developed the proprietary WaSP to perform these tasks. It is currently patent pending with the U.S. Patent Office. We have two unique versions of the WaSP. The original one we developed, we call the WaSP 1.1 or the blue, and you'll see why we call it the blue later. It is specifically designed for the DJI Matrice 600 Pro, which is pretty much the most commonly used, quote, heavy lifter UAV used in industry today. The WaSP attaches securely to the payload rails that are integrated with the UAV, so it's easy to take on, easy to take off if you want to remove it, and you put anything else under there, different cameras, different sensors. And with the WaSP attached to the M600, we have a payload capacity of 7.3 pounds. And with that, we have a flight time of around 7 minutes. So that is to reach the maximum payload of the M600 with the addition of the WaSP, we could raise and lower a 7.3 pound payload. The second version we developed that we call the Green, or the 2.0, was specifically designed for heavier lift applications. This one uses a Watts Innovation MFD 5000 as the platform. It's significantly bigger, more powerful, uses more batteries, all that good stuff, than the M600. And it is fully constructed of non-Chinese made components, so it meets the Secretary of Interior restrictions and DoD requirements, i.e. all the flight controllers, all the radios, anything that captures or transmits data is made in the United States. So we are fully compliant for any clients that may not want to have their data potentially transferred to foreign governments. We've incorporated a few additional benefits to this, since it does use non-DJI components. We put a LiDAR rangefinder, which is that little thing up on the front of the red arm. And this is not for doing LiDAR mapping, but it's for simply finding the distance to the surface. Because the Berkeley pit where we work is very large, and many times we're flying out about 1 kilometer away from us. So being able to accurately detect where the water is so we don't dunk it in the drink is pretty important. With the WaSP 2.0 on this, we have a payload capacity of 11 pounds and a flight time of approximately 24 minutes. I have that little asterisk there just because the payload of this drone is significantly higher. It can actually support an all-up weight of 75 pounds, but this would exceed the FAA regulations of a 55-pound weight limit. So in other countries where they do not have such restrictions, we would be able to raise and lower significantly heavier payloads by about 20 pounds. The controls for the WaSP, it's a platform independent plate. This is just a zoom in of the WaSP 1.1 on a little display stand so you can see it a little bit better rather than being tucked underneath the UAV. 2 people are required for the safe operation for sample collection. There's the pilot in command. This is the person that has the pilot's license with FAA. They control the UAV, they control the cameras, they do all that. And there's the equipment operator that controls the functions of the WaSP. And for these 2 devices, we have them operating on different frequencies. Now, since the 1.1 M600 version is on a DJI craft, the camera and the UAV controls are through DJI's Lightbridge, which uses 5.8, 2.4 gigahertz, and we've put in a 900 megahertz Airborne Innovations Pico radio to operate the controls. And you can see here we just have 2 little dipole antennas sticking out. When it's actually on the craft, those have wires that go up to antennas on the top of the craft. And the WaSP Heavy has slightly different operations just because or different frequencies used just for the ways that we connected to the telemetry and the flight controllers. All these give us a range of over 2 miles. So in the areas where we're sampling, we have full HD video, full telemetry, and full control of the WaSP apparatus. This is just a picture of 2 of us out there doing some water sampling in the pit. You can see the pilot in command, that's me. I'm operating the drone, and my assistant Brant is there with, he's operating the equipment operator, and he has a little field monitor that has an HDMI export from my video screen, so he can see exactly what I'm seeing with the pan, tilt, and zoom camera that we have installed on the WaSP. As I said before, the pilot in command operates the main controls of the UAV, operates the onboard FPV camera, flies the UAV out to the collection area and maintains the constant altitude above the water during the data collect, and then flies it back to the landing zone and lands safely. The equipment operator is, their job is to operate the function on the WaSP with a fully separate remote controller. They're in charge of the reel control, messenger deployment if we're using a Niskin or a camera water bottle. We have a safety line cutter in there. They can cut the line in the event of an emergency. And as I said, they can view the FPV output from the camera on the UAV. The primary reason for developing this was for worker safety. All sampling that we do can be performed well away from the hazards, which is contaminated water, cold water, unstable ground. From our sample location at the Berkeley pit, we're about 60 meters above the water, far back in a safe, flat area where we can deploy all our equipment. There are numerous berms, guards, so that there's no chance of tripping and falling or getting anywhere close to the physical body of water itself. Traditionally, water sampling, people always ask me, why don't you just use a boat? Well, the reasons why are, often it requires at least 2 boats, one to collect the samples, a rescue boat. You have to have many more people on the hazard or near the hazard. You need specialty training for working around water, and due to the thermal characteristics of the Berkeley pit or other mining pits, you may need cold water immersion suits and definitely personal flotation devices. It's more efficient than boat-based sampling. We could put the entire sampling kit in the back of a pickup truck and have it ready for deployment and sample collection in less than 30 minutes. And it's very rapid changeover between flights. You just change the UAV batteries, change the batteries on the WaSP if necessary, and then download the data from the data collection devices or transfer the water to be submitted to the laboratories for analysis. As a result, costs are decreased for sampling and efficiency is increased, and there are reduced personnel needed. We can do this all with a 2 to 3 person team. 3 people is preferred, but 2 is the minimum that you would need. We also think that it's the safest method for collecting samples using a UAV. It is powered independently from any of the UAV power sources, so we're not tapping in, stealing any propulsion power, which makes it safer so you can have, your full flight time with the UAV, and if we're pulling amps when we're reeling it up, you're not pulling those from the motor. The moving parts have guards or are protected by the rails to prevent pinch points. You can't get your finger stuck in there or get the lines stuck in the gears or the other moving parts in there. It's all tucked in, it's all safe. We've incorporated a line cutter, which is down in the lower right-hand side. This is a servo-activated guillotine-style cutter that the equipment operator can cut the line if necessary. So if we're sampling and our payload gets snagged on something, or if we have a problem with our batteries, we need to get the UAV back as soon as possible, we can simply cut the line. We lose the payload in the process, but we don't lose the entire package. The UAV can be retrieved and brought back home. Additionally, on the WaSP, we have a motor controller with feedback using a linear encoder that allows for precise control of the suspended payload, i.e., regardless of the weight that we put on there, it will hold it at those locations we want. We've programmed 3 different speeds for both of them, 1 foot per second, 2 foot per second, and 3 foot per second. And as I said, those are agnostic for payload. So if we put a 1 pound little, sampling device or a 3.5 pound Sonde, they'll both move up and down at that same velocity. And the safe part of this is that having that reel on there, we can tuck the payload underneath the center of gravity of the drone. So when we're flying out there or flying back, we're not what I call the static tether method, having a large, heavy payload suspended below the craft. And as you can see with that helicopter, if any winds pick up or anything like that, your payload can swing around, which we call the pendulum effect. And that is quite dangerous. It greatly increases the UAV instability. It makes flying more difficult and is often a cause for UAVs to crash. We have 5 different payloads that we've been routinely used for water and sludge sampling in the Berkeley pit. For water, we have a custom-made Niskin water bottle from General Oceanics. We use the hydrosleeves for performing water column profiles. We use a YSI EX01 Sonde. And we also have a small star OD that we use, a level locker, that we attach to the water collection devices so we know the exact depth where our water samples are being collected. And we're in the progress of testing a AMS sludge sampler for collecting sludge samples from the bottom of the Berkeley pit. This is a picture of the custom Niskin we had built. It's pretty much a free-flowing cylinder, so you have it in this open position, you lower it down into the water column, you lower it to your desired depth that you want to collect the sample. The water flows through it. When you get to your sample location, the equipment operator flips a switch on the remote controller. It drops a messenger, which is one of those two lead weights that are in the picture in that pelican case. That falls down and hits that white stopper, releasing those two stoppers, and then with tension, the sample is collected in there. The great thing about this is you can go down 100 meters, collect your water sample, pull it out. You're not having any water transfer all during that process of pulling it out. And even when you bring it out of the water, it's airtight, so your water is not getting affected by oxygen before transferring it to your sample bottles for collection. We also use a hydrosleeve. We were actually the first people to use this with a UAV. And the hydrosleeve group, after hearing feedback from us, designed a specialty, lighter weight, smaller hydrosleeve for use, and they commercially sell that now that a number of people are now using. We still use the original one with a 2-liter sleeve for water, so we can collect 2 liters with this. We primarily use this for doing surface water samples because it's just easier to fill it up than the Niskin. And overall, it's a lighter payload and easier to manage than using the messenger. It's pretty much just a plastic sleeve with a weight at the bottom and a check valve on top. You lower this hydrosleeve into the water. You bring it to the desired depth, whether it be surface or shallow in the water. That check valve on the sleeve is kept closed during that. When you're ready to sample, you rise it rapidly using the WaSP, or you can use the propulsion motors on the UAV, pulling it out of the water, filling it up. When it's full, the check valve closed, and then you can reel up your filled up water bottle to the bottom of the UAV and fly back. And as I said, we use a little star OD that we attach to the white cup on the top there for measuring the depth of the sample. This is just a little time lapse of some photos. And please note that there is a delay from where we put it in the water till when we sucked it up, because we did collect the sample about 5 meters down. But that just shows lowering the payload down into the water and pulling it back up. So that's a water sample, 2 liters we collected out of the Berkeley pit. One of our in situ methods of collecting data is using the Sonde. It's an advanced water quality monitoring sonde designed for extreme environments. On board, we have depth, conductivity, and temperature, dissolved oxygen, pH, ORP, and turbidity. And the model we got is go down to about 820 feet, which is about the estimated depth of water in the pit. Although we have not gone that deep yet with the sonde. Here's just a photograph of the WaSP lowering of the sonde into the water to do a profile. Star OD that I talked about, this is the small pill-shaped limb logger that we use. That was actually designed for use in fisheries and cetacean research in oceans. So they stick these in whales and other stuff and measure all kinds of parameters of them swimming around in the ocean. But we use it, we have a special container we put it in, and we attach it to the Niskin or the hydrosleeve to get the accurate depth range. So as I said, we can estimate our depth using the reel, but then we know the exact depth where these water samples were collected. And as a bonus, it's got a couple sensors on there, such as temperature, depth, salinity, and a sound measurement, which we haven't found any use for the sound measurement yet, but it collects that as well. And they're a company out of Iceland that manufactures these units. And this is our in-progress sludge sampler. It's an AMS sludge sampler. Typically, that little blue thing on the top of the metal cylinder would be screwed into a metal pole, and then it would be jammed into soft sediments or sludge to collect your sample. Unfortunately, due to the mass of this device and the resulting cylinder full of sludge, it exceeds the payload capacity of the M600. So this is only for use with our heavy lifter WaSP 2.0. The tips on that have those little flapper valves on that, so as it's descending through the water column and into the sediment, they stay open. We'll use gravity to embed it into the sludge. When you pull it up, the flapper should close and you should get a fully stratified sludge sample in that plastic cylinder. When you get back, you just put the caps on it and then you can send it out to the lab for analysis of the fully intact stratified sludge sample from the bottom of the pit. We've tested the weights of this, moving it around. We have not collected a sludge sample in the Berkeley pit yet with this. This is just a little video showing a water sample. I've sped up many parts of this at 10 times speed just so we're not sitting here, but this kind of gives you the scale of the pit and kind of the process of what we do. So there we just flew out. We got to our area where we wanted to sample. We're descending to the water. We're about 8 meters or so above the water. The equipment operator lowers the sonde. This is one with the the sonde. For here, our typical sampling procedure is to put the sonde in the water for a minute just to equilibrate. And you can see here we're moving normal speed. You can see the level line moving back and forth at the top and the gears turning around. This sample, I believe we were going down about 70 meters or so. So here we're going fast, zoom, zoom, zoom down. When we get to our desired sample location, we let it equilibrate for another minute. We found that if we don't do that, we get some hysteresis in the data, and then we pull it back up. You pull it back up to the UAV, you check with the camera just to make sure everything's all right. It's pulled up there, everything's good. And then you can simply flip your camera around and then raise up in elevation and fly back to your sampling location. So here we are, we're flying back. You can see the location where we do our sampling, how we're far away from the water. Here, then we put it in a hover, and we have what's called the catcher, stands down here. The equipment operator lowers the payload, whether it's a water sample, the sonde, the skin, whatever. They retrieve the sample, and then the equipment operator, once again, pulls up that line. So when we're flying around, we don't have dangling lines that can fly around and get caught in the UAV. This is simply just another video, and I'll cut out part of this, but this kind of just shows, this is taken from another UAV, just to kind of show the procedures needed for collecting a water sample. Once again, you fly out there, you go to your location, you descend down, and this also kind of shows the scale of this massive pit that we're dealing with. But due to time, I'll skip ahead over this. These videos are online on the YouTube channel. So look for Fairweather IT on YouTube, and you can see these videos in their entirety. But here, I'll just wait till we're at our hover here, we're above our water, we lower the payload. This is once again the sonde payload into the water, and then perform our profiles from that. Results. We've been out there 24 times and done over 104 individual flights at the Berkeley pit. That's a combination of profiles and water sample collects. We've got the deepest we've gone is 446 feet with our sonde. That is not possible using the static line method due to FAA regulations. And with our WaSP 2.0, we've estimated that we can put 1,000 feet of line, of our thinner line on there, which will allow us to do full profiles all the way to the bottom of the Berkeley pit. The deepest water sample we collected is 334 feet with a Kemmer, which was the older bottle that we've since retired due to it kind of leaked and didn't seal as well as the Niskin. Many samples with the hydro sleeves, and we've even done some depth sounding with the Star Roadie. So we just put the Star Roadie on the payload, flew out and lowered it till the line went a little slack till we hit bottom in a variety of locations to see, to do some simple bathymetry QA/QC. I can't share the exact results, but you can see a couple little profiles that we did last year, 3 different locations on October 11th. I guess that's 2018. And if you look at the turbidity one, where the orange line where it shoots far out, that is where we actually hit bottom by Horseshoe Bend there. It came up with a sludge sample from there as well. The data and the samples we've collected using the WaSP are used by Atlantic Richfield Company, their geochemical working group. This is a diverse group of geochemists, limnologists, water treatment specialists, and project managers looking to understand the mysteries of the pit. They use these data to create accurate models for the chemically changing Berkeley pit as it continues to fill with contaminated water and as water is removed for treatment and discharge using the new polishing plant, which you can see lightly in the background there. They've used our collected data to map geochemical gradients of solutes, chemical and temperature stratifications, and the regular overturn and mixing of the pit water that occurs twice a year. We share this data with Montana Resources, the Bureau of Mines and Geology, and the DEQ, and it supplements the Bureau of Mines and Geology's biannual boat-based water sampling. This just shows all the locations that we have sampled in the Berkeley pit, all the individual points where we've gone and collected sonde profiles, water samples, and so forth. And the WaSP could be used for not only collecting water samples, but there are plenty of other uses for it. Not only for collecting water out of mining pits, but for other maybe non-hazardous bodies of water. We've been in contact with some guys in Florida for doing some sampling of some old phosphate mine. They have these real shallow phosphate pits, I guess they're not pits, but bodies of water to sample water out, citing personal safety and cost savings. We've been in contact with a number of different volcano observatories around the globe. And actually the USGS and the DOI, Department of Interior, requested a personal demonstration, from seeing it in action. They want to use it at the pit lake that's developing at Kilauea. Right now they use the static line method and hydrosleeve, and they've experienced, when the weird winds blow up, they've almost lost a couple craft doing that. So for safety, they want to get away from the hazards of that static sampling and use the WaSP to safer collect water samples. Unfortunately, due to COVID, we were unable to travel down to Boise, where the DOI UAV center is, to give them the demo. But we are still in talks with that. And they're especially interested in the non-DJI version, since the Department of Interior is restricting use of non-US made UAVs for any type of data collection. We've also have some relationships with different UAV geophysical vendors such as GEM and Geometrics for raising and lowering their payloads that are magnetometers and radiometers. These you fly the surveys with it suspended below the UAV, but when you're flying out to your areas where you want to perform your magnetic surveys, there's no need to have the payload swinging below with that dangerous pendulum effect. And could be used, you could put a small bathymetry echo sounder on it, lower it into the water, and perform some simple UAV bathymetry in areas where you can't get boats to those locations. So we would like to thank phone companies for collaboration with this work. Atlantic Richfield Company has, they have funded and sponsored this project from the get-go. We're indebted to them for helping with that. We'd like to thank Montana Resources for providing access to the Berkeley pit so we can actually collect the water samples there. And Pioneer Technical Services and Copper Environmental, 2 other local contractors that greatly assist us with field work, safety, oversight support, and additional personnel when needed. If you have any questions, here's my contact information, or I don't know if anyone left any notes or anything like that, or if you have any questions, please ask them now and I can hopefully answer them.
Anyone have a question for Ian? Yeah, I try to give people a little extra time to type.
Oh, okay.
That's why I was just sitting here.
Let's
Please
see.
note that, contact information for all of the speakers is on the list of attendees. And so, oh, we actually do have a question. There we go. Does the WaSP float?
No, it does not. No, it is made of carbon fiber. The plate itself is a specially CNC'd out carbon fiber plate. All the materials that are on there. It's a brushless DC motor, and it's a modified fishing reel that we actually use to reel up and down. The little boxes that are underneath that are either green or blue are little custom electronics boxes that control that contain the voltage regulators, the radios, and the motor controller and the linear encoder to get the data back from the motor itself.
Excellent. Anyone else?
Yeah, so if the UAV in the system went in the water, it would be unrecoverable and would be a complete loss.
Here's a question. What are the weather maximums?
It is about 15 meters per second is what our cutoff is. That MFD, we could fly, that thing is so powerful, we could fly that at higher winds. But due to Atlantic Richfield UAV safety regulations, we cut it off at 15 meters per second. And we try and go out, and when we do our sampling during the summertime, we go out really early in the morning before any winds pick up. And if high winds do pick up or storms or anything like that does come up, we always err on the side of safety and would rather collect less data than collect more data and potentially have an incident or lose some equipment.
Another couple of questions. When do you need to return to the exact spot on the lake? Is this handled by GPS or another process?
By GPS. So, since we use two different flight controllers, it's much easier to do with the WaSP 2.0 since that's a Pixoc 2.1 blue cube. We can actually manually type in a waypoint and have it go back to the exact location. So we've done that before where we've gone out and done a Sonde profile, come back, looked at the data from that profile, and then the geochemist on staff has been like, I really want to get some water right at that inflection zone, or right where that, we're having some stratification. And we can go back to that precise location and perform the water sample there. With the DJI, it's more looking on the map. Your previous flight plans are shown on there. So you can fly out to the general location, but for the sampling. And then once again, you're about 5 to 10 meters above the water. There could be some drift with the sampling devices in the water, but with either platform, we can go back to the same location for repeatability, or if we wanted to collect a number of samples at different depths, or as I mentioned, to do a profile and then collect the sample at a specified depth within that profile.
And also, what would be the cost for doing a typical sampling run? How does this vary for doing bathymetry?
Well, what we've been with Atlantic Richfield, we've just been doing a simple day rate that we've negotiated with them. It really depends on how far we would have to go to perform the sampling, what type of sampling they want. But if you said we want all water samples or all Sonde profiles or a variety of the two, it wouldn't change the cost of that. The bathymetry using that what was I calling depth sounding. So it's pretty, it's we're cowboying it up. It's definitely not the most accurate way to get bathymetry, but for an area where you can't put boats in or there's no other real way to do it, it's kind of what we came up with. So we just use that depth from that start OD. When the line goes slack, we pull it up a little bit, and then we pull it out of the water, move a little bit to one side or the other, and perform the same thing. From that, we can make a grid pattern and then interpolate it into some kind of bathymetric surface.
Great. Good questions, everyone. Well, thank you very much, Ian. If anyone has additional questions for Ian, you can reach him via his email address that's on the screen right now.
All right, well, thank you very much for your attention. Yeah, please reach out if you have any specific needs you'd like to discuss with us.
Thank you. Okay, so moving right along, our next presentation is by Jimmy Voris. Jimmy is a geochemist and drone pilot at Golder Associates in Denver, Colorado. He manages Golder's US-based drone sampling practice. Recently, he co-authored a study on drone water sampling practices for mine water and the environment. When he's not deploying drones for environmental sampling, he develops water quality monitoring programs, as well as integrated water balance and quality models for clients all over North America. Jimmy has a master's degree in earth science from Dartmouth and a bachelor's degree in geoscience and engineering science from Tufts University. Welcome, Jimmy.
Hey, thanks so much. Is my audio coming through all right?
Yes, you sound great, and we can see your screen.
Great. Great. Well, thank you, everyone. Thanks for having me here at Mine Design Operations and Closure. And thanks, Ian, for that initial introduction to drone water sampling. Golder has worked in drone water sampling since about 2018 using the static tether method that Ian mentioned. We are currently working in about 10 pit lakes across the United States, and we're expanding to Canada, South Africa, and Australia. And I'm here today to talk to you a little bit about this work we did at Montana Tunnels with the Montana DEQ back in 2018, as well as some of the work that we did to validate this method compared to boat-based sampling, and additionally some of the new services that we're offering in the realm of drone environmental sampling. So really what I want you to take away from this presentation today is that first, in the case of Montana Tunnels and in several other cases since then, drone sampling has really met regulatory requirements for monitoring. And in the case of Montana Tunnels, it helped to alleviate some community concerns about environmental quality. Second, water sample quality from drone sampling is equivalent to that you would get from boat-based sampling. And finally, that there are some innovative sampling methods, some very similar to what Ian has been innovating in, that really allow for advanced geochemical characterization in pit lakes and help us to understand a fuller picture of the chemistry and sort of physical behavior of lakes, and more importantly, how they can be managed. All right, so the three locations I'll be talking about today are Montana Tunnels, right outside of Helena, and then we'll move to Thompson Creek down in Idaho. Bradley Kuchera, who presented here at MDOC last year, discussed a little bit of what we did with them to look at their pit lake. I'll give you a bit of a refresher there. And finally, some of the validation work we did in Dillon Reservoir, pretty close to us here in Denver. All right, so to jump into our case study at Montana Tunnels, just as a brief history to bring you up to speed, in 1986, the project, Montana Tunnels project, was approved and their operating permit was issued. This came along after the environmental impact statement was adopted, and this was where the first pit lake predictions were issued. And those pit lake predictions went through to closure or post-closure, and specifically we're trying to figure out or predict what the water quality would be when the pit lake reached equilibrium, when it was totally full. So from 1986 to 2008, Montana Tunnels, mining occurred at Montana Tunnels, was polymetallic deposit, and then in 2008, an expansion was proposed to the mine. The EIS was updated as a result, but mining stopped, and ultimately the pit lake began filling. And then until 2011, excuse me, Hey, Wayne. And then until 2011, the pit lake was sampled, and in 2011, the pit wall had its first major failure, which eliminated access. From 2011 to 2017, or actually 2018, the pit lake therefore was not sampled because there were these concerns about the pit wall's instability. And we'll go into a little bit of what this looks like momentarily here. But in 2017, because of the uncertainty relative to what the water quality, how the water quality was developing in this pit lake, some environmental groups notified DEQ of water quality concerns, and in 2018 the operating permit for the mine was suspended, which is when Golder stepped in and helped to sample the pit lake by drone. All right, so when we talk about the water quality here, I just want to put this in the context of what we can expect in the future. Screen's frozen up here. Here's the past 30 years, this timeline I just showed, and the pit lake predictions were made when the pit lake reached equilibrium. And so therefore there's 170 years or thereabouts where there's going to be evolution in the water quality. And what we're going to be comparing today is pit lake water quality in 2018 to pit lake water quality when the pit reaches equilibrium. All right, so just to give you a context of a little bit of a different environment than the Berkeley pit lake, here's Montana Tunnels flyover. Here's our drone. We're getting ready to fly over and take our water sample. I'm just going to stop it right here for a moment. So you can see that there's massive mass movement around the edges of this pit, and in particular, road access was partially removed in 2011, and then in 2018, as you can see, there was really no way to get down to the pit lake surface in a safe manner. And so when we flew right from here, which is a position of stable ground, out 1,700 feet over the pit and about 1,200 feet down, and sampled from approximately the center of the lake here, where we expected it to be deepest. All right, so I'll just let this play through so you can see this was where the road used to come down. So really impressive amounts of degradation along the pit walls here. And here is here's a video that another member of the or another employee of the DEQ, Jake Moorman, put together. This is a digital elevation model that he captured, I believe, using a smaller drone during that time, and it gives you a sense of some of the particular instabilities around the pit wall. And so as it zooms in here, I'll just stop quickly. So you can see some cracking along this aspect here. And then here you actually have segments of pit wall that are starting to slide in. So really, this gives you a sense of the impossibility of access. And as Ian mentioned, drones being a safer method of pit lake sampling, this gives you a sense of why. You do not have to send any person down to the surface of water. So it completely eliminates the hazard of people working on or near water, or even being in a pit. And just for reference, this is where that first video was taken from when we flew out over here, and there are no signs of instability here. And as another use case of drones, these digital elevation models can be generated by simple software and just GoPro cameras. So they're really impressive for monitoring this sort of instability over time and doing things like calculating volumes and the like. And as a final point, pit wall failures and landslides are the norm. they're not the exception in these cases. So here and in a few other mines we've been to, pit wall failures like this have really started within 3 years of mining stoppage. And so if you own a open pit, you can expect that there will be some degradation in that over time. So to go a little bit into the methods that we use the static tether method. And this is a site, of course, this is not in Montana, this is just one of our sites in Nevada. And what we really look for is rapid characterization and water sampling of pit lakes. So our first flight, typically we do a profiling flight first, not using a large multi-parameter probe, but instead a small contained conductivity, temperature, and depth probe that takes about 5 samples every second. And so as this falls throughout the water column and then come back up, we then bring it back, resolve that profile on a computer screen, and then based on a pattern, any patterns of chemical or physical stratification that we'll see, we'll target different depths in the lake because those different physical and chemical patterns can have significantly different water qualities. And then we send our hydrosleeve down. It's very similar to the method Ian described, and it comes back with 2 liters of water. We have a small thing called a microdiver, which is the same sort of depth validation Ian mentioned. All right, so all the subsequent flights, first flight is profiling, subsequent flights, we're taking water samples. So relative to the results that we got at Montana Tunnels in October of 2018, we weren't really sure what we were going in to check out, and what we found was that there had recently been fall turnover. We recognized that this was the case because the profile of the lake was essentially the same from top to bottom. So the temperature of the surface water was very similar to the temperature of the bottom water, and likewise the temperature of the specific conductance of the surface water very similar to the specific conductance of the bottom water. And where we sounded, that is the maximum depth that we got to was about 230 feet with the conductivity, temperature, and depth probe, and therefore we took 3 water samples, expecting to see that the chemistries would be quite similar, and lo and behold, they were. So across the water column, from top to bottom, we found remarkably consistent water quality. But more importantly, relative to community concerns, we found that no concentrations of any of the parameters we tested for, or excuse me, the MDEQ subsequently tested for, exceeded DEQ groundwater quality standards. And in fact, what we found was that most of the observed concentrations were below predicted concentrations of those parameters at equilibrium, except for a handful, which were above predicted concentrations at equilibrium, which were calcium, magnesium, sulfate, and zinc. But again, importantly, none above the DEQ groundwater quality standards. But as I mentioned before, and importantly, this lake is far from full, and relative to the predictions for the pit lake, there's been a different amount of pit wall failure, and that can expose rock of different geochemistry, which may change the ultimate water quality, the ultimate evolution of the water quality relative to the original predictions. And so that's why continued monitoring is important to understand the evolution relative to modeling and predictions, and that's why models need to be continuously on some reasonable interval updated and calibrated. All right. So to move on from the case study, I just want to talk a little bit about the work we did at Thompson Creek and at Dillon Reservoir, comparing drone sampling to boat-based sampling. And here are some profiles on the left and some water quality results on the right that we've done annually for Thompson Creek, and which were recently published in Mine, Water, and the Environment on a study of this method. And so what you'll see on the left here is two specific conductance profiles, one in November 2018, that's in pink, and one in June 2019, that's in green. And so you can see here that although there was not turnover during the fall or spring, there was a little bit down to 20 meters, so not full turnover. And this gives you the sense of why continued profiling is important, because you can resolve changes in stratification, but more importantly, you can see what remains the same. And as you can see here, both the profiles and water quality from samples we retrieved at depths of 10, 20, about 45 and 90 meters matched very well between the November and the June sampling events. And so our conclusion from this is that drone water sampling is precise. If we go back to the same place and we expect a similar water quality, that's what we find. And additionally, and this is based on work that we did at this Dillon Reservoir, we went out and we sampled using a drone and a hydrosleeve, and then we went and used a Van Dorn sampler. And we looked at the concentrations, and in particular, the difference in the concentrations between the drone sampling and boat sampling. So this table here shows the relative percent differences between the methods of drone sampling and boat sampling. And you can see that for all of the parameters, the relative percent differences were less than 20%, which meet EPA data quality objectives for duplicate samples. And so our conclusion here is that drone sampling using a hydrosleeve produces results which are as accurate as boat-based sampling. So not only is the method precise, but it's as accurate as boat-based sampling as well. And so therefore, for pit lakes, drone water sampling is safer because we're eliminating access to any sort of water surface. It's faster. Ian mentioned deployment times, and we realize very similar experiences to his. And then it's also cheaper than boat-based sampling because you don't need all of the boats, rescue crew, and all the equipment that goes along with that method. But most importantly, the data quality that we're getting from boats and from drones is the same. And so you can rely on this method to meet your data quality needs. If you'd like to read more about this in detail, our paper is available open access from Mine, Water, and the Environment, and I encourage you to go check it out. And our methods are laid out there as well, so you can implement this on your site if needed. And I just want to finish up by talking about some of the more advanced pit lake monitoring in the context of geochemistry and how pit lake geochemistry really can influence water quality here. So some of you may know, others you may not, but in lakes, there is often there's water that turns over year to year, and depending on how dense the water at the surface gets and how dense water below is, you can have a system that either fully mixes or remains stratified. Sometimes in mining environments, it's more likely to have a stratified or even a managed stratified lake, where some mining companies, for example, will pump brine into the bottom of pit lakes and tails as a method of storing these. And turnover and this stratification effect has a strong effect on dissolved oxygen through a lake, redox potential, and nutrient cycling. So it can really affect geochemical and biogeochemical processes within these lakes. And therefore, the water quality in a stratified lake at the bottom and at the surface can be quite different. And so it's important to resolve differences there if you need to manage this water. And then secondarily, precipitated minerals that come out of solution or amorphous solids can act as these sort of molecular sponges, and oftentimes we'll see that metals are scrubbed, quote unquote, by sorption or co-precipitation, and then they settle down to the bottom of a lake, and there'll actually be a large reservoir of metals stored at the bottom of lakes and sediments. And so, just to dovetail off some of the similar innovations that we're working with, we're deploying multi-parameter sondes in pit lakes as well. We actually just take a diver and attach it to our drone, and we send him down into the lake. No, I'm just kidding. We just simply attach the multi-parameter sonde to our drone, fly it out, go to a target depth, and hover. The sensors in these multi-parameter sondes take a bit to stabilize, and so we hover for about 2 minutes at each depth in the lake in order to get the best measurement, and especially dissolved oxygen and ORP are a little bit sensitive to the time that you keep it at a certain depth. And so with this gives us a good basis for creating a geochemical model of lakes, but oftentimes these geochemical models predict that there'll be precipitation of certain minerals or solids with associated sorbed metals. And so we've also developed a flight method with our hydrosleeve to capture sediments that we stir into the water at the bottom of lakes. And we've done this for one client, but as an example of a possible analysis of this sediment that can help to verify geochemical modeling, this figure above shows a SEM image of an algal cell. And then energy dispersive spectroscopy that allows you to develop elemental maps. So in a sediment sample, you can do SEM EDS and look at what elements are associated with different fractions of mineralogy or particulate matter. And it can really help you to get a sense of how your geochemical modeling is predicting what's going on in your lake. So combined with water sampling, these methods using multi-parameter sondes to resolve ORP and dissolved oxygen, pH, and importantly pH, and then sediment sampling allows us to measure all the parameters that we need to calibrate or validate pit lake geochemical models. And we're preparing another article on these methods within the next few months, so keep an eye out for that. And so I'd like to open it up for questions, but just to summarize, drone water samples were accepted for regulatory purposes at Montana Tunnels Pit Lake. We've also had them accepted in Nevada. And so we're seeing broader regulatory acceptance for this method. I think part of this is that we and companies like FIT have demonstrated that drone water sampling is safer, it's faster, and it's a lot cheaper than boat-based sampling for unstable pit lakes, and that data quality is preserved relative to boat-based methods. And then finally, we're really rapidly approaching a time where we can look at whole lake processes as opposed to just water quality from lakes to really get some insights and drive forward proactive lake management using drones as opposed to just monitoring. So if you have any questions, please don't hesitate to reach out or give me a ring. I can reply with a link to our paper, and again, it's available online here at the link that I shared earlier. So happy to take any questions.
Yeah, any questions for Ian? Or I mean, sorry, Jimmy, sorry.
No worries.
Lately, like I mentioned earlier, I've been trying to give people a chance to type. A couple on the earlier presentations, I think I jumped to the next talk too quickly, so. Okay, well, if anyone feels more comfortable just contacting Jimmy via email, his address is on the screen right now, his email address, and then also his contact information is included with the list of attendees. So please feel free to reach out to Jimmy for some additional information, and thank you very much. Our next speaker is Chris Brown. Chris received a bachelor's in watershed science and earth systems with a minor in GIS in 2017 from Utah State University. His interest with mined land reclamation began in 2017 as an intern for Monsanto on their open pit phosphate mine operations near Soda Springs, Idaho. After his undergraduate degree, Chris worked as an abandoned mine land construction inspector for the state of North Dakota during the summers of 2018 and 19. Chris is currently a master's student at Utah State University, working with the Utah Division of Oil, Gas, and Mining to evaluate coal mine reclamation in central Utah using unmanned aerial systems. So with that introduction, I will turn you over to Chris Brown.
Awesome, thank you. Can you hear me all right?
Sound good.
Okay, all right, and you can see that?
Perfect, yes, you're good.
Awesome, thank you. Well, glad to be here. Thanks for everyone. A lot of the presentations so far have been really interesting to listen to. So kind of just jumping right into it, a lot of the focus that I've kind of found over the last 4 years was using drones as a tool within environmental reclamation and remediation. And I've kind of tried to find a way to tie that in with the studies that I'd done before. As most of you probably are aware, using drones is usually kind of associated with detailed site records. There's a lot of different ways that we can do that. But something that I kind of started to focus in on is erosion and vegetation monitoring, and finding ways that we can kind of apply that more in what we do. And so in central Utah, they've been using a method that they refer to as pocking. It seems fairly unique. I don't really know if it is. Everyone in Utah doesn't seem to know of anyone else that does it. It's a really intensive process, but it's designed to reduce erosion, prevent runoff by capturing all precipitation or as much as possible before and kind of creating a micro catchment. From that, it then allows to promote vegetation within the semi-arid region. And most of the precipitation comes in monsoonal rainstorms. So they'll get most of their precipitation in 1 or 2 storms over the summer. There's sometimes a couple more, but it's a pretty limited amount of precipitation during the year. And they're usually about 4 feet wide or 1 to 3 feet deep. Let's see. So I'll kind of play this while you're, I don't even know if this is in there. But kind of from this, it's a really time intensive process. It's really expensive. As you can see, having an operator doing this, it takes months. Most sites, it's not recommended for sites larger than 50 acres. But they've been doing it for about 20 years. And so there's no real recorded study yet though on the actual effectiveness of this. The engineering's there. It has a lot of sites that have been reclaimed and their bonds have been released, but they kind of were hoping to get a better understanding of what's going on with these POCs. And so the goal of the project that I came on to was with the Division of Oil, Gas, and Mining here in Utah, to start evaluating pocking, looking at erosion, the vegetation growth, but then to also develop drone methods to monitor this pocking. And that would be in the form of a published technical report, a GIS tool that people would be able to use to kind of replicate that technical report, and then hopefully to aid in monitoring and inspections that they would have and with their inspectors. So the site that we kind of selected was Cottonwood, and then there's also the Desby Dove. They're northwest of Orangeville, Utah. They were underground mine sites, so not a whole lot of surface disturbances. They're in steep desert canyons. and they're kind of pinyon juniper sagebrush dominated regions. The reason they were both selected was kind of that they're at different stages. One's bond released, one is just recently reclaimed. They're within 3 miles of each other, and their geology, like everything's pretty much the same across the sites. The Cottonwood or Wilburg mine was also what it was referred to or known as historically. It opened in the 1890s, and then the reclamation was completed on the site in 2018. And so the Desby Dove mine site, it opened in 1898. The reclamation was completed in 2004, and it did have its bond released in 2014. So it's a good kind of goal for what Cottonwood should look like or will look like in the future. The drones we ended up using the DJI M210 with the MicaSense Red Edge M sensor attached. It's a 5-band multispectral imager. And also there's the DJI Phantom 4 Pro. The reason we picked that was it was a low cost, yet has a really high resolution camera for what it costs. And so with that, and it's also the idea that ultimately the state's looking to equip their inspectors with a fleet that they would be able to use within their inspections and possibly replicate monitoring processes that we develop, is kind of the end goal further down the road. What we use to kind of work with the drones, Pix4D has really kind of made a lot of really easy, simple solutions. Pix4D capture for the phone, we were aiming for a 1 centimeter or 1 inch or 2.5 centimeter resolution, had 80% overlap. We had to break up the flights into 3 different sets just over the site since because of size and also hazards such as cliffs and the elevation changes. And then that was all processed using Pix4D Mapper, which is a photogrammetry software package that's pretty efficient. So one of the big first issues that we ran into was ground control. GPS accuracy within the canyon is really difficult. It's remote, they're steep enough that you are lucky if you're getting a meter resolution with most GPS units. And so with that in mind, we kind of looked and kind of used the GPS, the onboard GPS within the drone and processed a run through Pix4D. And then from there, we were able to register boulders that were about 2 meters in diameter, and we used those as control for the rest of the imagery from that point forward. And that kind of helped us to reduce the error between the data sets. There were data sets that were collected before 2019 when we went out and flew, but there were a lot of issues that kind of happened with that. And that's kind of part of the challenges of this project. But we were able to get this orthorectified imagery from the sites. We were also able to get surface models from that imagery. And then we were also able to collect 1 year of multispectral imagery. And specifically, we were looking for the near infrared band that we were able to use to help evaluate vegetation later on. And all of this kind of went into a GIS tool that I've been programming and writing up. And the idea is to automate basic monitoring. It'll delineate the POCs, it'll detect erosion across the site, and it'll also just kind of do a quick vegetation analysis. So this was the first product that I was able to kind of get running with the digital surface models. You can see that we can identify individual POCs across the entire site. From that, I was then able to, there's over 30,000 POCs within the 22-acre site. That's probably a plus or minus due to some of the artifacts and kind of issues that I've ran into with this model, but it's still able to pretty well delineate where the POCs are. Running this on Desby Dove, as you can see, it's kind of the POCs are gone. It's kind of a mess. But if we really look at it, it's kind of replaced by elongated drainages, which is how we'd expect these POCs to erode over time as they go down slope. So it kind of gives a good idea of ultimately what the POCs will turn into. As we move forward with that, we're also looking at ground change using the surface model from 2020, subtracting 2019 from it, and we were able to get a change across the site. We were kind of, as we dive into it, the infilling was pretty easy to detect. Erosion was actually a lot more difficult than I would have expected right off the bat. A lot of this is what we've kind of decided on is that it's due to settling across the site. It's just recently been done. Slowly as time passes, it's going to start settling in on itself. And I also should note that there is about a 9-centimeter error between the data sets. And so as we're going forward with this, kind of knowing that yellow is basically the idea of no change, or we couldn't detect any change off of what we had. And then going from yellow to red is where the elevation is lowering or evacuating or erosion. And then going from yellow to green is then it's increasing in height or it's filling in. And so the general erosion that we're seeing across the site, generally the POCs aren't changing. There are locations where they are, at least over these 2 years, but the edges, we can kind of identify that they are eroding as expected. If you kind of look within the spot that I've kind of highlighted here, you can see that there's a darker orange surrounding the lower level, and you can kind of see it around in the rest of the POCs. And that kind of shows that the edges of the POCs are eroding, closing in on themselves. They might not be detectable at where that they're infilling, but they're still, we can see that they are eroding in the way that we would have expected. That's another example of that here, where you can kind of see that there are sides of the POCs that are eroding into down slope or up other ways that I kind of tried to verify on the ground eventually. So kind of if we dive in, there's kind of some areas of interest. Right here, we can see that the POCs are starting to elongate, similar to what we saw in Desby Dove. We can actually visibly see that erosion happening across the site. Here's another kind of cross section showing the 2019 POCs versus the 2020. And it kind of validates what we're seeing across the site. There's this one of the second one that we were kind of looking at. There was no real visible erosion when I looked at the 2020 imagery, and I was kind of trying to figure out what was going on. It also kind of showed some deposition up in that upper edge along the side of the edge of the site. And if I kind of zoomed in on that, I realized that a lot of that was tumbleweeds from Russian thistle, or like there were Russian thistles that had dried up and broken off and were flowing around. And that makes a lot of sense to some degree because the site had quite a bit of it last year. And then these POCs are a lot bigger. It's also kind of an abrupt change between offsite to the POCing. And so that's something to keep in mind as we're kind of working forward with this tool and with these evaluations. We also, that's kind of another kind of showing that like there isn't really much difference between 2019 and 2020. There's a little bit, but we just can't quite determine that from the air. Number 3 kind of dives into it where it's live vegetation. Since it's a surface model and not an actual elevation model, vegetation will cause errors across the site. It's not necessarily a bad thing, but it's something to keep in mind as we look around, since the POCs aren't changing, but they do show that they are increasing in depth, or they are increasing their height, I should say. So if we kind of go into area 4, there's no real visible erosion, but it's also some of the deepest areas that we've got. It shows, and that's kind of what started getting the idea of settling. We'll notice that a lot of that is all along the channel. And that's kind of what we find consistently across the site, where that riprap channel that they've put through the middle of the site is about 5 feet deep. And so with that, we're pretty sure that a lot of the sediment's kind of settling down into that over time. And that's kind of what we're seeing. But something, well, and then if we move on to kind of a last area of interest, pretty sure that this is possible error from image processing. The imagery wasn't the best in this location, and it kind of shows where it's got kind of a really high increase in change, but increase in elevation, but yet there's no real evidence to support that across the site, or at least across this section. So moving on with kind of the products that we're kind of trying to work with and create for this, we use the multispectral imagery to run a normalized difference vegetation index, which is kind of a common way to evaluate whether vegetation is growing versus bare ground, and then also trying to get an indice on how well you can evaluate kind of how well the vegetation is growing as well. We just used it for basic yes or no of vegetation, and that requires the multispectral imagery, so you have to have a sensor that has that equipment. With that though, we were able to determine the vegetation distribution across the site. It's kind of an interesting idea where you can see that it is validating that they are growing within the POCs, just as we would have expected and what we've seen in the past. So to kind of verify all this, I ended up going on the ground. I collected 200 ground observations across the site, or over 2 years. And that was using mainly the idea of looking at erosion. Could I measure it? How much was happening? Getting pictures of what I'm seeing, conditions of the POCs, looking for general site conditions, and also just kind of doing a general vegetation distribution across these POCs. To kind of supplement that, we were doing 43 rebar stakes or sediment gauges that we were installing. This was to kind of do a consistent sample of the evaluations, and then also have kind of we just took the difference of the ground from to the end of the stake. So we knew if it was 74 centimeters one year and then it was 72 the next year, then we'd be able to understand that it had risen 2 centimeters. And then ideally we would compare this to the ground change over time. One of the big issues is GPS error. This was one of the sediment gauges that I installed. It's definitely not where it's supposed to be according to the GPS. And we're trying to find a workaround with that. We've just recently kind of decided that we're going to manually move them and then just kind of buffer an acceptable area around it to kind of try and get the average change. And then also kind of compare that with some other ideas that we're coming up with to look at change over the POCs in general, from like the highest elevation of the ridge line to the lowest location that's marked within the POC. This would be the idea of what that would hopefully do. This is an example of where it's actually seems like it's been fairly successful, where the one sediment staff or gauge of 16 measured 12 centimeters in the field, and we were actually able to evaluate and find that in the ground change, it was saying about 14 on average in that area that we buffered around it. So still off, but still pretty close to what's happening on the ground. Also with ground verification, we've been noticing that there were some areas that were over like 60 centimeters or over half a meter of difference, and those were kind of excluded as outliers. But when I actually dove into some of these sites, you could actually see that there was visible erosion happening. And this was in an area that was settling quite a bit right along the rock channel. And it kind of makes sense on the ground once you see it, that it's like, yeah, it definitely was falling. So it's kind of things that you have to keep in mind, that you have to be looking for. This isn't a catch-all solution, but it's definitely a way that can help understand the site better. This is another validation of one of that site one that or area of interest that I kind of showed you. Definitely all the POCs are full, they are flowing down, they're kind of eroding through, which is kind of interesting to see once it's actually in action. So a lot of these challenges that we've been running into, there's a lot of data issues that we were running with. There were coordinate systems that one person would use that someone else didn't use. We had some people trying to use LiDAR. Some of these, like they wanted us to use this 2017 imagery, but there's no way for us to actually correlate that or align that up with any subsequent imagery. And when we asked for raw imagery, no one had any. Apparently everyone got rid of their raw imagery because it does take up a lot of space. But something that I would kind of recommend if anyone's going to do something similar to this is keep your raw imagery, or at least request it from contractors or whoever else you have doing it, because it can really help further down when you have issues in a project. Also, some other challenges that we ran into were site conditions and timing. In this area, you have no idea if a storm's coming in on you. We took the drone up, and then we had a snowstorm come in on us, and this was in May of this was last year. And similar things to this all happened quite often. There wouldn't be anything in the forecast. You'd be out working in the field and suddenly there'd be a rainstorm that'd just be dumping on you. That doesn't really help with drone flights. Also, the length of the study. 2 years is not enough. We can't go from 2019 on the Cottonwood site with POCs looking like that and understand exactly how they get to the 15-year mark with the DESB Dove POCing. And so kind of as to wrap up, the data shows the site is generally working as expected. It's pretty well understood that it is successful in the long run, but being able to kind of see this in action using drones was really something that was we've been found is quite valuable, but it does need a longer evaluation period. And then also better ground verification is something that we are definitely going to be working on, and then also kind of encourage the Utah Division of Oil, Gas, and Mining to move forward with. And we can see that the methods definitely can provide accurate site records, but not only that, they can detect major erosion events, and they can identify the vegetation growth and the spatial distribution across the site. And with that, I think I somehow talked really quickly through that. But yeah, I'll take any questions.
Any questions for Chris? There we go. Can you elaborate on any general error you can apply to your measurements or a minimum measurement for accuracy?
Can I see that chat? Could you repeat that again? I'm trying to just kind of.
That's okay. Can you elaborate on any general error you can apply to your measurements or a minimum measurement for accuracy?
Are you asking about just like the aerial imagery with or with like the ground imagery? Like, I'm guessing you're talking about the aerial imagery. I just kind of looking for, let's see.
Let's see.
Related to the DSM.
Yeah,
Related to the DSM. Okay. Yeah. So, I mean, as general error, it really depends on the system. There's always going to be error. It's one of those things where you fly a drone and you use GPS, there's going to be some amount of error no matter what. The goal is to always minimize it. And one of the things that I was hoping to do with that kind of registering with the boulders is working to just make sure that as long as the sites or the surface models from each individual flight are as close to that original as possible. So, I mean, there's not really any general error we can apply. I mean, the 9 centimeters is kind of what we settled on because we kind of looked through, if you take the ground control points and you look at what the error, like what one elevation is, and then what the elevation is on the second round. So 2019 value to the 2020 value, you'll then kind of look at the averages, you kind of look at that data and you're able to determine that like there's this much error within that, if that kind of makes sense.
Thank you. Yes, the gentleman who asked the question said yes, thank you.
Yeah.
You also just had a comment that says a similar process to pocking would be dozer basins used in Montana on steep slopes.
Yeah, I'll definitely need to take a look at that because that's something that like when I've done the research, like deep gouging is really like everyone kind of knows that's a method that you can use and kind of what it does, but it's definitely something where it seems fairly unique, but I needed to take a look at that because yeah, it's one of those things where as you're continually looking for it, if other people are doing something similar, it's nice to know what they've seen.
Yeah, exactly. Any other questions for Chris? right. Well, thank you very much, Chris. I appreciate it.
Yeah,
Great
no, thank
talk.
you.
Anyone has any questions for Chris after the fact, you can contact him via his information on the list of attendees. Thanks, Chris. Okay, so moving along, our next presenter is Mike Rawich. Mike is a geologist and a geographer specializing in the implementation of geospatial technologies to optimize environmental problem solving. As operations director on Rambo's Gallego team, I hope I said that right, his focus is on remotely sensed data analysis, collection, and visualization applied to mine site investigation and remediation. Gallego uses aerial imagery and image analysis to understand site conditions, reduce uncertainty, and help efficiently characterize sites for environmental risks. Mike is an Interstate Technology and Regulatory Council team member and is a co-author on the ITRC chapter for advanced site characterization tools. He is also a certified Federal Aviation Administration remote pilot and is a senior unmanned aerial system operator within Rambo's Global Drone Practice Group and serves on industry advisory boards at Kansas State University and the University of Kansas for his expertise in unmanned aerial vehicles. So with that, I will turn the microphone over to Mike and let him get started on his presentation. Thanks, Mike.
Thanks, Susie. Can you hear me and see my screen okay here?
I can hear you, yes, and I just see your logo screen right now. Is that
Okay,
what...
great. Great. All right. So first off, I just wanted to make the point that this is a really great session. This is one of the first conferences I've been at that has this much focus on unmanned aerial vehicles as a new technology. It's been really fun to see all the great technical presentations, and really it's an honor to be included in this. So thank you for organizing and to all the other speakers contributing to this session as well. Today I'll be speaking about the work that my team is doing on behalf of my team, and really talking about some of the innovative service offerings we're trying to develop for land monitoring, both in mining, and I have a case study actually outside of mining, but which translates back. This is a good transition, I think, from Chris's presentation right before, because we're using drones in this case to look at rasters and as a remote sensing instrument, as opposed to an extension for in situ measurements. So specifically during my presentation, we'll touch on some commercial aspects of my team's organizational structure and how we operate. And then we'll look more at drone imagery analysis with a case study, and then satellite imagery analysis with a case study as well. So generating understanding and monitoring around lands generally has some universal pain points. It's an expensive process which requires manual boots on the ground surveys routinely, and it's very difficult to track quantitatively over time. Additionally, when you look at things year over year, it becomes even more difficult, and it's difficult to muster the resources needed to provide early warning of significant problems when you're dealing with large area land management. And so providing early warning of challenges before they become major issues is a common complaint among land managers across the globe. This is where Gallego comes in. We're trying to solve these pain points using what we believe is the next generation of land management technology. Gallego itself is a flagship program for Ramboll and our digitalization and innovation spearhead. Ramboll, it's a global engineering and design consultancy company headquartered in Denmark. We have more than 16,000 experts across the globe, and we work frequently across interdisciplinary networks with these experts in fields of water, ecology, and environmental engineering. Ramboll's a global consultancy in environmental engineering, and the way our relationship is structured with them is they've invested in our technology through their Innovation Accelerator program. So this program is actually the company's own startup accelerator It's similar to what is frequently done in Silicon Valley for venture capitalists looking to invest in high growth technologies and businesses. The year we participated in this accelerator program, we've been launched for about a year and a half now, and we were we were the top idea out of 270 ideas that applied for that accelerator program. Our service generally works with 4 components. First, we inventory the site using either drone, aerial, or satellite data, and there's a number of criteria that go into selecting whether one of these tools is more appropriate than the other for data collection. We then use a suite of tools, most of which are driven by artificial intelligence, to actually analyze for various risks or concerns we have across the site. And then as you repeat these measurements over time, you can monitor how your site is deteriorating or improving across time. The last bit that we combine by working with expertise in Ramble is we can then provide recommendations on how to improve or continue to increase efficiencies from the results of our reporting. So remote sensing in general provides value as we see here. The 4 main areas that we find for our clients is that, one, you get a complete picture, really every square inch of your site, and you're able to do this safely to characterize and analyze the entire site, not just a small sample as you might get with many on-the-ground methods. This includes even the most remote areas or the largest areas, which helps to make recommendations from this type of analysis rigorous and reliable. Second, I think we find that there's a lot of value in removing human error from this equation to the extent possible. So by having digital data, performing quantitative analysis, we can remove subjective error where it's appropriate. And oftentimes our clients have previously unseen insights from these types of analysis, that things that are very subtle or either difficult to access for various reasons, they've never seen it before. And after they perform this type of analysis, they have a new understanding of their land that they manage, their mining site, and how that can change over time. Having a digital copy of your site, and this is sort of what Chris looked at as well, that you can look at it over time and begin to try and detect where some of these issues become subtly changing over time, and even some of the larger events you're able to check very quickly. And probably the last chunk of value that we see on a routine basis is using the technologies that we're discussing here. You can reduce time that you spend in the field. You can't completely reduce the amount of time you spend in the field, but you can make your time in this field more effective, and you can spend your resources more efficiently. So with that bit of context to where we typically see value for our clients and sort of how we operate, I've got 2 case study examples to go through here. The first is a vegetation reclamation monitoring project where we use drone imagery data and analytics. This site is in the American Southwest, and this is typical of something on the order of hundreds to thousands of acres which require monitoring. Really what we did here was to be supplemental for SMCRA. We worked with both the regulator and the client on this portion, which is going to be incorporated in a phase 2 bond release package, with the idea that in the future we can use this to reduce the number of transects that are required on the grounds, and help them decrease the costs that they have for bond closure over the long term. So we'll begin by looking at some drone imagery data here, and to give you scale on the bottom left, you'll see that scale bar is equal to about 500 feet. So this is really crisp, fine resolution, spatial resolution imagery data, similar to the kind of data that we looked at with Chris a couple minutes ago here. So there's actually several hundred images that are stitched together to create this one orthomosaic image. And if we zoom in on this inset here, you can again get an idea of what the quality is for this one patch of shrubs located on the site. Through this photogrammetric process, and again, Chris did a great job of setting this up and demonstrating some of these processes, you can also get an elevation scan of the environment here. And so not only do you get an image of the plants just based on its color, as you would see to the naked eye, but you're also able to detect what the plant structure is generally, what the three-dimensional structure of it is. But you're not only able to do this across for just one plant, you're obviously able to look at the entire site and pick out where there's minor elevation changes across the entire site. The third piece of information or data, input data that we had from the drone in this case, was actually looking at multiple spectrum imagery, and this is a vegetation index similar to what Chris had on the last slide, or the last presentation as well. So we're looking at near infrared and how that can tell us more than what you can see with the naked eye. And again, you're able to look across the entire site in this case. This is the beauty of drone data, is you capture a tremendous amount of data very quickly. The challenge with drone data in many cases is being able to then analyze that data in a meaningful way. And it's getting to the point where if you're performing weekly drone flights like we are with some of our clients, handling all of this massive amount of data in an efficient manner and getting useful information out of it over long-term changes over time is very difficult. So the method that we've elaborated for, that I elaborate a little bit for here, is where we take different input data. So in this case, we're taking spectral data as we looked at, elevation data. We're combining that with information we have about what we know is actually on the ground, or training data. We process those two things together using a machine learning algorithm that provides us a predictive model which we can then bring future data into. And the result you get is labeled data. We do this all programmatically. The screenshot on the right here is a video, which in classic e-conference fashion is not functioning for me at the moment. But it shows our Python environment where we've done a lot of the custom programming we have here. And so you can handle large volumes of data automatically with routine workflows like this. So going back to our customer problem here that we have in the American Southwest, the SMIC monitoring that they have here occurs over thousands of acres. In this case, they're using linear transects across these small areas, and they're using those to determine vegetative cover and invasive species and how that affects their vegetative cover metric. That's the main metric they have to be in accordance with their phase 2 reclamation bonds release in this case. So they want an overview of the entire site, but the resolution of imagery that they take for regular mine reclamation activities through aerial or satellite imagery is just too coarse in this case. And so we proposed a pilot study with them where we actually collected very high resolution multispectral drone imagery. An example of what that kind of looks like is shown here on the screen. And then using the process we just described, where we input elevation data, spectral data, and training data together, we developed a machine learning model to classify what land types are across this whole area. For those of you less familiar, machine learning is just a way that we teach a computer. It's a type of artificial intelligence where we teach a computer to look for a specific signal and associate that with a value. So in this case, I can kind of flip back and forth here. This is what our classification algorithm did for this subset of the data. So you can see in the bottom left here, we have 5 main classes that we've categorized this into. You have bare soil, rock, which in this case is actually exposed mine spoil, and you can see that as some of these rocky debris that are through here. Shrubs, grasses, and then we sort of have this generic class of other vegetation that we still need to refine down. And what this allows our client to do is to get a general measurement of vegetative cover over time. They can begin to look at things like, all right, if I need to go back in and fill in these areas where there's exposed mine spoil with topsoil, what's the area that I'll need to bring in? What's the volume of topsoil that I'll need to bring in? How much has been eroded from the site? Those types of questions we can begin to answer. Not only that, but they can break out percent vegetative cover, which again is the main driver for reclamation activities at this site. And they can look at how that changes between growing seasons. So they can go back out. It's been delayed somewhat because of COVID and travel restrictions this year. But the idea being we can go back out this year and show that vegetative canopy cover is stable or increasing from year to year. And we could go back and do this for as many years as required in the permit to inform the regulatory process and really improve our understanding of how this particular portion of the site is improving. Same site, but a different location. Those of you who live out west, I'm in Kansas City myself, but I've become familiar with this reddish brown grass you see throughout the image here. Again, we're looking at percentage of vegetation cover, and unfortunately for our client in this case, cheatgrass counts against their vegetative cover requirements. It counts as an invasive species, and so if we zoom into an area here, we ran the same type of algorithm to actually classify where cheatgrass existed and come up with the metric of how that's affecting the vegetative cover in total across the entire site. So the results for this client are still preliminary. Again, we've been keeping this very above board, working with the state regulator in this case, who's in charge of the permit, and also working closely with the client throughout this whole process. So it's kind of a trifecta to get this project completed. The next stage that we're going to go through is actually reviewing the data, providing a copy to the regulator, reviewing this with them, and hopefully performing a second round of analysis as we come to the end of the growing season here in 2020. Our client will be applying for a phase 2 bond release, and both the client and regulator in this case have agreed that this could be supplemental information to support whatever information we have from a vegetative transect series. So that's our first case study here, and the second case study I'd like to present here is one that I've actually decided to change since we submitted our abstract, because we've had some significant project developments with this exact project. This isn't in the American West, it's not mining, but I think you'll see how this technology and science directly applies to many of the challenges that we have in managing large infrastructure problems associated with mining or managing large areas of lands that are associated with mining. In this case, we're looking at a very large area, several hundred square kilometers, that we have to repeatedly monitor, and so we chose a satellite-based monitoring approach that we'll dive into more. Specifically, we're working for the client of Highways England in this case. Highways England had a specific challenge where they have to monitor habitat and land cover change along their entire road network. And for perspective, this is equivalent to, I would say, the interstate system in the United States. That's what this is a public entity of in the United Kingdom, except for they're responsible for monitoring and keeping track of their entire environmental estate and making sure they're in accordance with specific land cover goals related to biodiversity net gain. So we are developing an intelligent environmental state for Highways England. And we're doing this using a constellation of satellites called the Sentinel-2 satellites. These are 2 satellites that are operated by the European Space Agency. They have a revisit time of every 2 to 5 days. And unlike drone imagery, they have a very coarse resolution, 10 meters, whereas drone imagery, you're usually dealing on the order of 5 to 10 centimeter spatial resolution. This data you're able to actually grab. So the satellite flies over every 2 to 5 days. It downloads it to a cloud-based server, and then you can programmatically access that information and do this all in the cloud. So you never have to download data itself. You can maintain it all in a cloud infrastructure system. So that's what we've done here. We've selected this multispectral satellite image, which flies over every 2 to 5 days, and plugged it in. And we're dealing with a significant amount of data here, which is why that cloud-based information is important. What I mean by the cloud is this is all done on a server. You never have to download it to your local machine. And this is an example of what the road network looks like, and what these bounding boxes are that you see on the screen is what we're grabbing along the entire road infrastructure network. Each one of these boxes represents, less than a gigabyte of data, but we have lots of these boxes, almost 2,000, and we grab them on a routine basis using this programmatic method that we developed. And so, we save a lot of time, a lot of effort, and gain a lot of extra value by being able to do this not on a local machine, but on a cloud-based server, and by being able to grab this programmatically, automatically, not having to do it manually at any means here. So for this particular client, we began developing a prototype in 2019 and have continued this development here in 2020, where we can now look at network-wide habitat change. So we're looking at land cover change here. And by the end of this year, we'll have a prototype demonstration in an operational environment, including a web-based delivery. So we'll have basically a web app you can log into with your browser, and then you can investigate this data and query it. Similar to the same approach I showed you before, we actually take ground-based training data. They have a database that the ecologists have been building for years, and we combine that with the satellite imagery data that we collect across time, and we tell a machine learning model, this is the signature that you get for various habitat types. And so this is sort of how this works here. So we have these ground truth areas. We're able to go in, grab data over time. We can then integrate that all on the virtual machine network here. So it's all on remote servers. And then we're able to deliver a model out the back ends. And in fact, we're able to test many different models simultaneously and see which one's the most effective. And then we can generate, this is what sort of your final product looks like. We can generate a map showing what your land cover type is across the entire network. What's really kind of innovative about this and special is that traditional approach, you might take an individual image, your satellite image, and classify it. But what we're able to do here, because we can go up and grab each time the image is captured, is we're able to look at basically a 4-dimensional data cube of this site, which really improves the efficiency and accuracy of our model predictions here. And to elaborate a little bit more about what that means is, wetland classification is sort of a classic problem that people in this type of science run into. Because we're able to look at multiple time steps, or this 4-dimensional data cube, a wetlands might look just like a lake at a particular point of year. On another point of year, part of the year, it may look exactly like a specific type of vegetation. But if you're actually able to look at how that wetland changes across the year, you can pick out a curve, a spectral curve, which correlates very well with a wetland in a particular environment. And so we've been able to increase our accuracy, in this case, to 95% or above in comparison to ground truth data for a lot of these models here. So it's really exciting stuff, different clients, but when you care about monitoring large tracts of land over time, this is one of the most efficient ways that you can target a program for moving forward. So coming up on the end of what I wanted to present here, I love this quote from one of our clients, which is that we're now making maps we've never been able to make before. I think we've seen some of that in the session here today. But this technology that we're utilizing, combining technologies like drone and satellite imagery, and looking at GIS and using artificial intelligence analysis, these are real things that we're combining together to solve environmental problems in a way we've never been able to do before. So it's very exciting to be a part of that and to be able to present on it here today. With that, I can open up for any questions that might come in. And here's my contact information on the screen here as well, if you'd like to reach out.
Any questions for Mike? That's a gorgeous picture on your last slide there.
Thank you. We need the Jeopardy theme song going here.
Yeah, I know.
There's a piano back
Yeah, we do have a piano. Okay, all righty. So no questions for Mike. Okay, well, people, if you think of something after the fact, please feel free to reach out to Mike via his email. It's on the screen right now, and it's also on the list of attendees. And Mike, thank you very much. I greatly appreciate a wonderful presentation.
Thank you. Pleasure to be here. Thanks.
Thanks. I have to get Okay, so we're just a few minutes ahead of schedule now, but that's not a problem. I see that Gage is online and ready to roll for us, so I guess we can go ahead and proceed with the introduction for our last speaker of the day. I would like to thank everyone for participating all day long. Hopefully you've enjoyed the presentations today. I think we've had a great slew of talks. To finish us out for the day, we have a presentation by Gage Zobel with Dorsey and Whitney. Gage has been a presenter at our conference before, so I'm sure some of you may remember him from the past few years. Gage is an attorney with the law firm Dorsey and Whitney and is based out of the Salt Lake City and Missoula offices. Gage was born in Dillon, Montana, and raised on his family cattle ranch in the Big Hole Valley, where he still maintains a small herd of Black Angus and Charolais cross cows, I guess. Gage focuses his practice on various aspects of natural resource, water, and environmental law, and regularly practices in North Dakota, Montana, Wyoming, Idaho, Utah, and Nevada. His varied experience includes securing access through public land, assisting clients with the National Historic Preservation Act, and navigating clients through compliance with the Endangered Species Act. Gage also regularly assists natural resource companies permit, secure, and defend their water supply through the Intermountain West and Great Basin regions. So, with that introduction complete, I will turn it over to Gage and let him take the floor.
Thank you so much, Susie. Let me just see if I can get my PowerPoint pulled up here with sharing my screen to make sure that works for everybody. Your screen sharing.
Yeah, I can see your screen now.
Perfect. Let me just open it up here. Can everyone see that?
Yes.
Okay, perfect. Well, Susie, once again, thank you so much for letting me present. I move my notes over here on the side. So I'm going to give an intro, but I think you gave a better intro than I ever could. That's my bio from the website, and from as long as it was, I apologize. I should probably cut it. I'm very thankful we're still able to do this. Thankful for the opportunity to be here. In particular, I think I gave a presentation last fall at the Pacific Northwest International section that was on Circle 108B and really the preventative measures of what we could do from it coming back. And I spoke with Susie afterwards, and we thought we could update that presentation and perhaps it would be of use to here today. And so with that, I've just entitled it, what is an ounce of prevention worth, in reference to Circle 108B. So I'm going to start with this picture here, and pardon me for sharing that. This is my new son. This is Theodore, and I bring him up for a very particular reason. If you look at the bottom right-hand corner, you will see that my PowerPoint, as put together by our Minneapolis folks of Dorsey and Whitney, still has PNWIS. I've been on parental leave, and I just got off parental leave today for 14 weeks, and so the true ounce of prevention is that I should have probably prepared more beforehand, and I apologize. I thought the conference had been canceled, and so I was in contact with Susie last week as I was going through around 1,200 emails, catching up before I came back to work, and saw the conference was still on. So truly the prevention here that I'm going to be speaking about should have been taken by me beforehand. With that said, I do want to talk a little bit about what type of ounce of prevention and what type of pound of cure we're discussing when it comes to Circle 108B. I presented on this 2 years ago at the Montana Tech Conference. And the reason we're bringing it up again today is I think there's some very relevant issues. When we look at it, there are minimal effects and efforts that can be made by industry and by state and local regulators that honestly will be able to prevent massive effects to industry as well as the local regulators in years to come if they make them in the interim. And the prevention that we're really looking at, and we'll hit at the later part of this presentation, is state regulatory reforms, industry practices, and then when agencies are going through their informal rulemaking, what they can do to prevent reversal of agency decisions. what that does in the long-term effect is prevent this pound of cure, this negative effects that are affecting all of us. That's when we get one-size-fits-all federal regulation that may not necessarily work for the industry and honestly is duplicative and displaces through preemption different areas of state regulatory regimes. It's solving negative public perception with the mining industry generally. It's solving continued multi-million to billion-dollar cleanups that occur across the industry. And finally, the backlash of agency reversal on their own rules. So I've got a picture here of us beating a dead horse. Right before COVID hit us, I was at a mining conference in Lake Tahoe back in March, and a former colleague I used to work with at Crowley, Fleck, and Billings was presenting on Circular 108B. And I remember someone from the audience calling up at him saying, you know, you presented on that 2 years ago and last year. And the joke was, why do you keep bringing up this issue? And so I guess we should really address that right off the bat. Why are we beating a dead horse? With things like NEPA 2.0 and the reforms that have been going on, there's a lot of regulatory issues that could be discussed, which are incredibly relevant to the mining industry and could have been presented today. But I thought the analogy, or the analogous situation rather, between 2016 to 2017 and the current situation between 2020 and 2021 really highlighted why we might want to discuss this. You know, number one, the mining industry and state regulators dodged a bullet. Circular 108B really, as it was proposed at first, wasn't necessarily the best fit. That's personal opinion, for resolving the residual issues that still affected the mining industry. So we can learn from how we avoided the proposed Circular 108B rule to understand in the future how you're able to avoid similar one-size-fits-all not good regulation. But also equally important is the idea that we are literally an administration change away from an EPA reversal. And in light of a potential EPA reversal of an administration change, what is the likelihood Circular 108B comes back or comes back to us in a different form? Hence why we're going to have this topic today. You know, with the rest of my time today, what I'd like to be able to really focus on is the history of Circular 108B, which I assume that most everyone here knows about. But in case someone doesn't, I'm going to give some brief history, I'm going to give some background, give the timeline of what occurred to bring us up to the present situation. We're going to talk about what the pound of cure proverbial was, what Circular 108B as a proposed rule was going to do, how it was going to work. We're going to discuss what the preventative measures that had been taken by local industry, state regulators especially, other federal administrative agencies, and by industry itself that was able to prevent that cure from taking place. And then we're going to talk finally about applying that in the future and how that works and the potential for an EPA reversal in the upcoming years. So with the history, you know, Circular 108B is something that was promulgated with the first circular legislation that went through Congress. So back when it first came out, and this is the statutory interpretation here, within 5 years, not before, the president needed to promulgate requirements where he would go through and look at different facilities and establish, consistent with, important here, degree and duration of risk associated with those industries, basically bonding and reclamation regimes, ways to make sure that the Superfund wasn't going to be overcome with onerous amounts of different fundings and sites coming on board. And so he's going to look at that and see what they would be able to do to put forward regulations and classifications for future bonding. And so we jump into our timeline, starting in 1980, which was before I was born. And then by 1987, I'm a year old now, we've had the SARA amendments to CERCLA. We've changed CERCLA a little bit. We've changed financial responsibility, and we've started doing some delegation. And in particular, Executive Order 12580 changed the proper individual who was going to promulgate these rules from POTUS, and it moved it over to the EPA administrator. So we pushed that down to the EPA administrator and gave him the authority that he could promulgate the rules, review financial security, assurance bonding, which is what Circular 108B is all about, reclamation bonding, and he'd be able to make that determination. We've gone 7 years already. It could happen at any time. But instead, we have a 22-year gap from 1987 to 2009. And that doesn't mean reclamation bonding is not going on. What it means is that it's really pushed out to the state and federal agencies. So things like BLM and the United States Forest Service, and locally, local state agencies that have to bond and have to permit mines really have to take on the workload. And you have some issues that are, you know, I'm going to say catastrophes, things that are negative to the perception of mining. I'm most familiar with Montana. You've got Pegasus Gold. You have Zortman Landusky. Things happen and states have to make changes. And in light of this dearth or this vacuum of federal promulgation of rules, what you have instead is you have states stepping up. And so that's the situation that you're in literally until about 2009, when you have NPOs push forward and push for litigation to say, look, EPA, you really need to move forward and promulgate rules like you should have 20 years ago, 25 years ago. And with trying to be generous to the situation, there were still issues they were seeing. We had residual cleanup at mines. They wanted to get that addressed. At least that was the open face of what they were doing. Openly, the court sided with them in 2009. That was the Northern District of California. And the Obama administration didn't appeal. It instead took that under advisement and moved forward with identifying priority classes of facilities that they would start to look at for reclamation bonding. And the first of those facilities or classes they looked at was going to be hard rock mining. Again, we have some delay. 5 years go by without a proposed or final rule coming out. And so litigation once again pops up, and EPA is sued to finalize its CERCLA 108B rule. And that was the Idaho Conservation League et al. There was multiple other parties that pushed for that. And in May of 2015, the court ordered that a mining rule had to be established under CERCLA 108B. And the proposed rule needed to come out in December 1st of 2016 with the final rule of December 1st, 2017. So by the summer of 2016, a proposed rule had been formulated by EPA, and they very well sought input from the small entity representatives. They discussed what were we missing, how did our formulas not work appropriately, and the SEERs honestly did a lot of background information, put a lot of information forward to show that in many ways the proposed rule was going to be duplicative. It really wasn't necessary. Along with that, we have something big happen in November of 2016. Some would say it was an unexpected change. Although we knew the Obama administration was going to end, I don't think it was fully predicted that the Trump administration would take over, would move into power. And so at that point, we have an immediate moving on January 11th. And if you look, the final rule was supposed to come out December 1st, but the Obama administration pushes it forward. And right before it turns over to the Trump administration, it pushes out a final rule and has a 60-day comment period. At the end of that 60-day comment period, the Trump administration extends the deadline for public comment. And now we're in 2017. And as that public comment goes out, there's whispers going out that the Trump administration is going to do a 180. And although the final rule wasn't enacted, it was just proposed, they were going to make a change and probably push forward for a no action alternative, or basically say that the only rule they needed to promulgate was no rule because it was unnecessary or unwarranted due to the degree and duration of risk. And that is exactly what eventually happened by December 1st of 2017. By February 21st, CERCLA had its final rule published, it came out, and immediately we go once again to litigation. I mean, attorneys have loved this. So we have suing, first of all, for FOIA requests of information, basically trying to find what information had been provided to EPA that would make them change their mind. And in 2019, those lawsuits eventually ended up in the DC Circuit Court of Appeals under the Idaho Conservation League v. Wheeler. And the DC Circuit Court of Appeals ultimately ruled in favor of EPA and said, look, EPA's interpretation of the statute and its need to promulgate rules or to go forward with the no action alternative was appropriate in light of the evidence that they had. And that's where we were at. And so at this point, I think last year, everyone kind of thought this was over and this was dead. And it probably is. Let's hope the dead horse is dead and we don't have to keep beating it. With that, there was additional schedules that were pushed out. So other industries to be regulated would be the electric utilities, petroleum and coal, and the chemical manufacturing industry. And they had proposal dates for their own proposed CERCLA 108B rules to come out respectively in July 2nd, 2019, which did happen. Another proposed rule for the petroleum and coal product was to come out in December of last year. It came out. In every situation, a no action alternative was once again proposed by the EPA. But a change, and you can see again the idea that we might have an administration change occurring happened with the chemical manufacturing, or Industry 3, which had a scheduled proposal date to be December 1st of 2022. And instead they pushed that up and they pushed forward their own proposal just this year. Once again, a no action alternative in February 21st of 2020. And you can see, very similar to what the Obama administration had done previously 4 years ago, the Trump administration is pushing forward to try to get final rules on the book to make it harder to overcome a potential challenge or agency reversal in the future. So that's the background. Boring, we go through it. I really want to focus then, what was this pound of cure that we were really going to be looking at for hard rock mining? And we could spend hours going over it. I don't think it's really the point of our presentation today, so I'm going to try to be a little more brief with this. Really, the proposed rule under Circular 108B that the Obama administration had proposed was you were going to have standard health assessment costs of over $500,000, $550,000, that would be assessed at all sites, that would have to be bonded out. Natural resource damage, NRD, would be a set amount that would be tied to your resource response costs, and it would be tied at 13.4%. And the response costs themselves would be based on a formula. In a nutshell, it was going to cause additional bonding. They were unsure if they were even going to allow corporate guarantees. EPA's preference was corporations would not be able to have their own guarantees. It would cost the industry roughly $7.44 billion in bonding that way. Financial liability was going to go up. There was issues with where they were going to have publicly available bonding, who was going to be supplying that. And finally, I think that the biggest issues that were really bothering people was how fast you had to come up with the money. Within 24 months, your health assessment costs had to be bonded out. Within 3 years, 50% of your response costs in the NRD would have to come out. And within 4 years, the remaining 50% of the response costs in NRD that had been calculated. I don't have those numbers in front of me, but I remember looking at an example of something like Pebble Creek in Alaska, and you were looking at orders of magnitude higher in their bonding regimes under the formulas being presented, 10 to 20 times higher. And so it's just much, much larger amounts of money that needed to be bonded for, which in turn was going to cost industry. It was going to put a bind on the individuals that were going to be the guarantors under the bonding regimes. And things that were additionally perhaps scary, less sure for industry, there was only a discretionary release of the bonding. So under most state regimes, when you're able to get your bonds released, you show that you've done your appropriate reclamation work and the bond's released. Here, any bond under the federal regime would only be released after notice and comment period by the public. So you could open up another set of litigation that could go forward. And ultimately, these things were all these pounds of cure that industry didn't really want to have to face. And honestly, state regulators were worried about as well, with the idea that their own bonding regimes would be preempted under a federal regime, under federal statute. Hence what industry did, or the preventative measures that I don't think industry or very especially state regulators ever really thought of when they were putting in commonplace changes over that 22-year gap from 1987 to 2009. And what they really said is, look, when you look at what you're proposing under the rule, it doesn't make sense because we've taken preventative measures. One, the level and degree and duration of the risk isn't there anymore. The overall cost to industry, the economic effect, was going to be around $115 million. That was going to be hitting the pocketbooks of industry. And that was only to cover an estimated roughly 15 million of unfunded cleanup costs. It was a cannon killing an ant. It just didn't make sense. Honestly, the biggest issue as well, it's duplicative. You know, you've done nothing for 22 years, but just because there was nothing done for the 22 years under the CERCLA statutes, other federal agencies, BLM, United States Forest Service, state agencies and state regulators stepped up and filled the void. And as much as maybe industry may not have liked that for those 22 years it was happening, it was good because they filled the void that had occurred and they were solving the issues that were being experienced on the ground. Finally, the duplicative nature of what was being proposed could be preemptive of the state bonding regimes. I think another issue, in economics by my background from undergrad, so this matters to me very much. You have a very small market of individuals that offer bonding, the guarantors. You don't offer under basically free markets in that situation. It's an oligopolic structure. And so when you suddenly increase the liability that they were going to be exposed to under the formulas, where they would have to be on the hook, you were going to decrease the suppliers into that market. And it suddenly became a little dangerous, a little scary. Are we even going to be able to have people that are going to enter into the bonding market? And if they are going to bond hard rock mining, at what cost are they going to raise to industry? This 115 million cost we looked at actually could have become much higher. And finally, the issue for industry that was preventative is you had bad evidence that was affecting an outdated problem. In honesty to the Obama administration EPA, as they promulgated a rule, they were solving issues that were early 20th century, late 19th century mining issues that needed to be resolved as we were cleaning those up. But they weren't solving the problems for the modern day 21st century mining, which has dramatically changed. Industry has gone so far forward, and therefore this rule wasn't really necessary. You're solving an outdated problem. EPA looked at the preventative measures. Ultimately, as we decided, said, look, no rules necessary. We're not going to impose additional financial responsibility requirements under Circular 108B. We think the states have it. We think the other federal agencies have it instead. And the quote that perhaps matters most is they said, look, EPA has reconsidered whether rulemaking supports the proposed rule in light of EPA's interpretation of the statute. We're going to hit that in a second. The review of the record and the information and data received through public comment. And so the comments that received and the information and facts that came in enabled them to do the reversal that they had from the Obama to the Trump administration. Under the statutory basis, and this is what I really highlight for everyone, is what the state regulators did, and honestly what industry did, were the preventative measures that enabled the federal agency to be able to back off. One of the comments that was made was that EPA believes that it is consistent with congressional intent to consider state laws before imposing federal financial responsibilities. Therefore, Congress did not mean for EPA to disrupt existing state programs that were already successfully regulating industrial operations to minimize risk. So the DC Circuit Court of Appeals came out and said, look, you've already handled it, and we don't want to step in the place of states. And that is a kudos to the state regulators, because over the 22-year gap, they took the preventative measures that were necessary to move things forward to prevent the need for any additional regulatory regimes that would have additional bonding. In return, the second quote as well from the DC Circuit Court, despite its focus on currently operating facilities, the proposed rule relied on a record of releases of hazardous substances from facilities and payments to respond to such releases that does not present the same risk profile as the modern facilities to which the rule would apply. Basically, look, industry has modernized. And the rule that you're proposing today, we can see why you want to now do a no action alternative, because it doesn't address how modern mining works. Things like this conference discusses, where we're pushing forward that mining isn't done 18th century anymore. It's done in a 21st century, very highly technological way, where some of the old resource damages, the old reclamation bonding that would be needed for the damage to the environment isn't necessary. It's already handled. We've gone past it. Industry's far cleaner than it ever used to be. And so this was their basis for their decision. Ultimately, they looked at the individual things that came in through the administrative record, which is where industry and state regulators both put forward ideas on, look at the evidence, look at the actual facts, the dollars behind what's being spent on reclamation bonding, look at the additional regulatory regimes. And that was really an evidence report, a releases report, and practices report that were the basis for the DC Circuit Court of Appeals decision. And ultimately, I mean, I want to push on to the end here. Those are the preventative measures that happened. And because of those, EPA had the justification it needed to do an agency reversal. So with the remaining time that we have, and I started early, so I don't want to take us too far later, but for the next 10 minutes, what was that ounce of prevention truly worth? Untold amounts. Billions, at least $115 million a year to industry is what the ounce of prevention over 22 years of industry innovating and changing, and 22 years of state and local regulators finding common sense solutions in their own state regulatory regimes to address this issue. And the three things I want to focus, as we talked at the very beginning, is regulatory vacuum. When we see regulatory vacuum, what we need to do, and you have to have state regulators, local regulators, and federal agencies step in so that you prevent future onerous regulatory burdens from applying. You have to identify areas where regulation is not, And I'm going to push at industry here. Instead of seeing where you're able to squeeze by because you don't think there's a proper regulation in place, don't, quote, make hay while the sun shines. Instead, what you need to do is identify that and say, look, maybe we're not regulated, but we can go above and beyond. And by going above and beyond today, it might cost us a certain amount of money today, but in the long term, it's preventing us from building a narrative that will result in an onerous regulatory regime that's going to be put on our back. That goes back to industry adaptation as well. Look, industry needs to prevent bad actors from moving forward with bad mining practices. They don't help anybody. And honestly, advance the technology to a state that some of these issues that are being observed are honestly obsolete. And that final ounce of prevention is one that's looking towards the future. And it's how do we defend from agency reversal in the potential that they decide to do so within the next year or the next 2 years, depending on an administration change. So first of all, the regulatory vacuum, turning the lemons into lemonade. I think, you know, for state regulators, the lemons of agencies, federal agencies not stepping forward and putting forward their own regimes is that it falls on the states. And the states have to do it. The states have to be the ones who take on the additional burdens. But honestly, that can be turned into a good thing for the states. I think Nevada's done a great job. I think Montana, in its own way, has done so as well with their own state regulatory regimes, specifically dealing with bonding. And the same's true, I think, for industries I just mentioned above. You know, don't take that there's no regulation from industry as a way for industry to run rampant. Self-regulate. And that's really turning what could be a potential bad situation in the future to something good. And so honestly, those two parties need to work together. I think one of the amazing things that we saw when we were fighting the Circle 108B was that you had state agencies sending in letters alongside the local industries that they were regulating saying it was unnecessary. And where you might traditionally have two parties that some people would think would be opposed to each other because they're constantly working within a state, they were very well united because they knew that the regulatory regimes that had been put in place in the states and at the local level were working because they'd done it together. And so in light of other situations where we see federal agencies basically hamstringed by their own political agenda, which happens because federal agencies are caught between administration changes. And because of that, you've got shifting priorities. I think it's a perfect opportunity for the state regulators to look forward, to work hand in hand with industry, and vice versa for industry to identify areas that might need regulation and say, look, if we work together, we fill the gap. And when that gap is filled, because we've worked together, we resolve a future problem for both of us. And that also goes to the idea for industry adaptation. Picture here the Stillwater mine and just how beautiful it looks generally. Look, necessity is the mother of innovation. And we've understood that in environmental work for years. You know, we've got best available technology, work with that under BAT and so forth. When you push industry to make changes, industry innovates, industry gets better. And I think the same thing's been happening with mining for years. If there's a cheaper, better, more efficient way to do things, we're going to figure it out. It saves us money. It saves us money on the back end with having to do reclamation and cleanup. So no one wants to do dirty practices. And that innovation and that adaptation by an industry, if it's properly documented and taken head on, horns forward, really resolves some of the problems in the future of onerous federal regulations. Some people talked, maybe industry needed to do a tax and put this minimal base tax that would refund Superfund to cover them. I don't think that's necessary. You know, I think industry adaptation and moving forward to cleaner technologies, cleaner ways they do work, more innovative things on how you design, how you operate, and how you reclaim your mine is resolving a lot of the issues. And when a new issue pops up, it just needs to be addressed. Along with that is calling out bad actors. You know, I think the problem everyone has is when they think of the mining industry today, they don't think of modern mines and how clean and how advanced and technologically improved they are. They think instead of 1800s, they think of, you know, the Golden Sunlight mine, Sunnyside, down in Colorado that I worked on, which is an 1800s mine. And they think of the damage that occurred there, not realizing that's not modern mining. A lot of these issues aren't modern mining. And when you do have a modern mining company that's doing bad practices, you know, and we get issues like Zortman-Landusky up in northern Montana, that has to be called out by industry. If industry recognizes that and distance itself from it, they're able to later on defend themselves to show why they are better than those own bad actors. And honestly, it just shouldn't be put up. And the final idea of industry adaptation, which is preventative of future regulation, is self-regulating. Look, put your own self-bonding regimes in. Make sure that the reclamation isn't done necessarily on the cheap. You do it to the satisfaction so that all parties are happy. And that resolves issue for future projects that you want to open up. Go forward with good neighbor agreements. We've seen great issues, Stillwater Mine's done that. When you work with community and you work with local regulators and you self-regulate what you yourself are willing to do and how you're going to operate, it might feel like you're being hamstringed minimally, but what you're really doing is building a partnership that mitigates the risk of future regulation because you've already put regulatory regimes in place that basically put off the need for a regular agency to come in later. And with the last minutes, I want to talk about, so what is the threat of an agency reversal in Circular 108B? The reason that I think this topic is most relevant today. How likely is it? And before I go into it, I probably should have started this with a caveat. I don't want to be political. I think people that have heard me speak before in other situations probably know my politics, but that's not my place here. I don't want to get into politics. I think every administration brings positive things. I just really want to look at how administration changes change things. And so without making any political commentary, I think we can look back, if you look at the timeline I gave you originally and say, look, between 2016 to 2017, you had a complete reversal in EPA from their proposed rule to the final action rule that came out, which was a no action. And the catalyst of that truly is a change in administration, a willingness maybe to look at other information that comes forward. And right now, there's a likelihood, a chance, I'm not going to jump in and say how likely it is or not, but it's still there. Polls would say it's likely that we're going to have another administration change at the end of 2020. And we're going to do that again. And we're going from an administration change that'll probably be more similar to what the Obama administration enacted as opposed to the Trump administration. And so under the real possibility of administration change, we have to start looking at, are they going to change their priorities? And are they going to bring back Circular 108B? Could they bring Circular 108B back? And is that a foregone conclusion? So I think, first of all, you need to highlight, there's some differences. In 2016, you had just finished a proposed rule, and then you very quickly, the beginning of 2017, before the administration changed, pushed in a final rule. At this point, we already have a final rule that's in place, so it makes EPA's ability to reverse course potentially slightly harder. I'll give you some of the statutory law in a second on how they're still able to do so. You have an established record of decision. That's very helpful. With that, we've already got facts that have been laid out, that have been reviewed, have been litigated multiple times. And so an agency changing course, it's easier to argue they're being arbitrary and capricious. Further, there might be far easier way for EPA to address residual problems. I think a lot of water treatment. I think that's really what this was all about in the end too, was long-term water treatment. So is there other ways EPA can address what they think might be outstanding issues with long-term water treatment without relitigating an issue that is, as we've talked about, a dead horse? And further, I think there's an opportunity for the mining industry that's different now from the past to show, look, mining is necessary. Under an idea of a Green New Deal, you're going to need so much copper, just for instance, that you'd have to mine all the copper we ever mined in the world twice over again to be able to promulgate that idea and those policies. Mining's essential. We need the mineral resources in many different ways, let alone the industrial minerals that we're going to need to move forward. And so are we really going to want to hamper an industry that's essential if we're going to be moving forward into a non-petroleum type world? So in the overall answer to the question, is it likely? I don't know, but what I can tell you is it's possible. Under case law, EPA could reverse and decide to move forward and re-bring up Circular 108B. I don't know how likely that is. I think the likelihood's contingent on if they think there's other ways they can address the outstanding issues, such as long-term water treatment, which has been brought up multiple times as something they're wanting to address. The case law behind that's really in Encino Motorcars versus Navarro, and agencies are empowered to amend or repeal their existing rules. And the no action alternative is an existing rule. They're able to do that so long as they provide a reasoned explanation for why they're doing that change. On the contrary, they can't repeal rules that were mandated by statute or by judicial order. So I think that the first preliminary issue you'd have to address is EPA, the agency, is it merely a policy initiative that was under their discretionary authority to push forward the no action alternative? If so, that's reversible. If instead you're saying, no, this was mandatory statute to have to put this rule in place and it was mandated by judicial order. Guys, I just don't think that's the case. If you go back up to what the DC Circuit Court of Appeals said when they defended EPA's decision for the no action alternative. They said it was based on their discretionary authority to determine what the degree and duration of risk is. So under that, I do think there's an option and the ability to reverse agency action and to about face again and maybe try to repromulgate rules. If they decided to do that, if that was EPA's best way, they think, under a new administration to address these issues, they'd have to go through a new round of notice and comment rulemaking, the same way they promulgated the original rule. And so the issue then would be, okay, if the agency is going to reverse course, that's what we're concerned about, what standards are they going to apply if we're going to challenge back? And it's still going to be the arbitrary and capricious standard that most of us are familiar with, where the agency is going to have to prevent or provide essential facts, a basis, a reasoned decision for why they're changing course, literally 180 degrees from no action alternative back over to maybe additional reclamation bonding in a different way. And that agency decision cannot be an illogical outgrowth or cannot be based on inconsistent reasoning. And that idea of inconsistent reasoning is why it's so great that you have an administrative record that's been put forward under past litigations that show all the reasons why bonding regimes are not necessary right now, above and beyond what's already at the state level. The final issue that'll really be key on this is if there's a heightened standard, and there might be arbitrary capricious standard plus is what it's referred to. And what that's going to go under is the idea of, number one, agencies are going to have a harder time reversing, one, if they don't display an awareness that they're changing their position. 180 change is going to be obviously a displaying of their position change. If they don't show good reasons for their new policy. And three, this is where industry has the ability to have an ounce of prevention. If the new policy rests on factual findings that contradict those that underlie the prior policy. And that's what you're really going to need to show is, look, we can show you through history and 22 years of work with state agencies and with bonding that this really isn't justified. The facts just don't supply it. Or if you're able to show that the previous policy that was enacted has had industry rely on it. That usually takes decades. Right now, we're only dealing with 4 years, 3 years. So that's probably a harder sell. But you could probably get a heightened standard to be able to stop an agency from reversing course if you can show that the factual findings they're bringing forward just honestly don't contradict what has already been put forward in the previous administrative record. And ultimately, I think that's it. And I think my time, I've gone over 35 minutes, but I started early, is our issue. Look, obviate the need for regulation. Work with your local regulators. That's my push to industry. Be happy your local regulators are working with you and they want high standards. Maybe it's costing you more money today. It saves you money in the long run. And ultimately, if EPA decides to reverse course, which is possible, I think we just have to keep our eyes open for it. Be prepared for more notice and comment rulemaking, where you're going to have reasoned, documented, and factual comments. And as you provide those forward, you're going to have to build the basis to show that any change is going to be an illogical outgrowth of what the industry has already shown to exist. And that would be the ounce of prevention you can do today to stop the pound of cure of more federal regulation in the future. And with that, thank you. It's the end of the day. It's a boring legal presentation, but thank you for staying with me and for listening through it. And I appreciate that opportunity. And I'm happy to take any questions if we have any that have to go forward.
Okay, Gage, if you look at the chat comments section, you have several quite lengthy ones. Normally, is it a repeat? Okay. So it says, excellent presentation. EPA started out on a different path, but it got turned into something that was not recognizable as financial assurance. Would it make sense for the state and federal agencies and industry to consider a common financial assurance guidance, or is the future to continue to have relatively different approaches?
Let me read it to you. I heard it, but I barely pulled this at the same time. Whoa. The chat. So I'm just reading this again. Would it make sense for the state and federal agencies and industry to consider a common financial assurance? Look, I think that's a good point. I think, wow, so this is a personal opinion, guys. I think baselines are good. I think baselines help. So I do think there is some idea and it would make sense for state and federal agencies to consider common guidance. And I would say baselines, base levels, not ceilings, obviously, but basements. I think that resolves issues, because you could never say that certain states aren't meeting up to their guidelines or meeting up to what you would say would be a federal level. But I think the moment that you start putting on a mandated structure that everyone has to follow, I don't know if that works. I think states are different. I like that. I think an example of what just happened under Circle 108B, a lot of what they looked at is what Nevada did. I think Nevada does a great job. I think Montana does as well. I don't want to criticize Montana in that, but states innovate, and I don't want to take away the ability of states to innovate and then have other states saying, hey, that's good, we're going to borrow that and we're going to adapt our own. And that's the problem. If you make everything a common approach, I don't like that. But if everyone got together and put a common baseline on the bottom, look, these are just guidelines that every state, industry, everyone agrees on has to be met, I 100% agree. I think that's perfect. And I think that also resolves issues for the future with being able to have agency reversal, a federal agency reversal, or future challenges, because what they're really going to try to highlight are those issues where a different state or a different agency or particularly a different industry is not meeting up to the high regulatory standards they want. And so if you have a baseline everyone's meeting, you resolve that issue. You take that argument away from them.
And then there is a second part to that question that begins, the lack of consistency is potentially still the most problematic issue from the public perspective and from the standpoint of argument that this is still an issue. Could this be an effective way to preempt future 108B arguments?
Yeah, that's what I was trying to say before. And I think that the individual makes the comment, I think he's right on. I think like I said again, the level and the degree that you want to make the consistency across the board, I think that's going to be, well, I mean, you're stepping on states' toes and industry's toes. But I think, look, it's a cost-benefit analysis. If you want to completely remove a lot of the risk, you need to have consistency across the board. So it's just the level of risk that you want to mitigate. I do think if you had some commonplace structures and guidance in place that every industry and every state followed, you resolve a lot of those issues. And I think further what you resolve is a lot of issues that the public has, that mining's basically dirty. And I've never understood that. I think mining's actually very clean. I think the best things, everyone should go take a mining, go tour mine. I think that'd be good for them. Like, feel the same way with cattle. Everyone needs to go visit my cattle ranch to see how we free range cattle and cattle work. It's not this dirty industry we necessarily think. There's always issues that have to be addressed. So I think fighting public perception is above and beyond having common sense guidelines that are shared across the board. I think it's also about the mining industry stepping up and showing its own industry adaptations. But if mining industry does that and you have some consistency across the board and highlight that the lack of cleanup that's occurring is not modern mining but past mining, I think you resolve and preempt most of those arguments. So I agree mainly with that comment.
I liked your answer. You have another question. You mentioned NEPA 2.0. What are your thoughts on the revamped NEPA?
Guys, I should spend more time with NEPA 2.0. So, you know, I'm at a firm that's big, and so I do some NEPA. I love it. We've got other partners that do far more work in NEPA, so they would know better than I. So I'm gonna have to jump off them. I like limiting regulation, and one of my biggest issues with environmental issues has always been environmental regulation. Is the job is to find a way that we can move forward with mining or anything if it's clean, if it works. And the purpose of NEPA is not to kill projects. It's to go through a policy and through a procedure to make a determination on how we can move forward with it best, if it can be done best at all. And so we have to consider things. What I think NEPA had turned into was 10 years of lawsuits that you could never get through. And ultimately you were drying up funding for projects. And that's not the purpose of the statute. That's not the purpose it existed for. And you've turned it on its head. And I don't like when any party turns a statute on its head. So I do think NEPA 2.0, I think the revamping tried to address some of that. Its effectiveness in doing so, I don't know. I haven't done enough litigation on it myself right now to really speak. But from what I've seen, the study I've done and the limited work I've done in Wyoming that deals with NEPA 2.0, I've liked it so far. I think it's better. I think it resolves some of those issues I had of arduous and onerous timelines that just honestly weren't necessary. I think agencies can move quicker. At the same time, I think you're running the risk with NEPA 2.0, where you're cutting down the timelines that agencies have to pump out decisions, that you're not getting a fully considered, reasoned decision that considers all the alternatives. And when you're doing that, you're also opening yourself up to the potential for additional litigation. So I think maybe there has to be some interplay. I don't think NEPA 2.0 is perfect. I think it has to have some revisions, but in many ways I liked where it's gone.
Excellent. Any more questions for Gage? Okay, well, that was an excellent presentation, Gage. Thank you very much. It's a wonderful way to finish out the day. So thank you very much.
Oh, my pleasure.
I want to thank you. Bet. Thank you. Oh, wait, you did have another question come in. Is there a country with a regulatory model you would like to see the U.S. move towards?
Look, I don't do international work. Dorsey does. We do a lot of work in China and in Canada, a lot in Canada, as well as Australia. We do some work for the Australian companies. I like Canadian model. You know, I've worked with some people from Blake Cassell's, and when the Canadian model comes forward, they address a lot of the same issues we address. But they seem to do it in a more timely manner. I don't ever really see them going for the type of duration that we're going for 10 years, 20 years. 20 years might be exaggeration, but a good 10 years, 10 to 15 years to get a project off the ground. It doesn't seem to happen there as much. And they seem to have just as good of input from, you know, First Nations, Indigenous peoples. They seem to be doing it very well, to the point that when they come and they try to open up a mine in the United States, I work with an Australian company that does that. They're shocked that it takes so much time. So I'm not going to say I want to fully adopt the Canadian regime. I don't know it well enough, but I think it would be good to look at their model and see, in many ways, they're considered a more environmentally conscious nation than the United States. I don't know if I believe that, but at least have that reputation. I would like to look at what they're doing that seems to be making their stakeholders happy and still being able to get through the process in a timely manner so they can open projects. And maybe we should take some things from what they're doing and apply it. All right, good call. All right, good call. Yeah, 20, maybe it's not an exaggeration.
Yeah.
I just don't want to be harsh. It's not an exaggeration. I think honestly, regulation, if it's not 20 years, it's a death sentence sometimes, which means it's like life in prison for the project. So you're right. But to the first question, yeah, I love America. I'm not trying to say take Canadians, but I think they're doing something right up there, at least to please their stakeholders. And we could look at that. And I think that would be something we could look at to maybe revamp things in the United States.
Anyone else? I think we could talk about this topic for a long time. Okay, well, thank you very much, Gage, once again, for a wonderful presentation. And thank you for concluding day 2 of the Mine Design Operations and Closure Conference.
Thank you.
So I just want to remind everyone that tomorrow is our last day. Yes, we are going to connect via the same Zoom link that has been previously sent out. So same time, same place tomorrow. We'll get started at 9 a.m. We will be done midday, just as we normally would be if we are out at Fairmont. We'll be done around lunchtime. So thank you very much. Please make note of our wonderful and generous and supportive sponsors and get in touch with them if you see fit. Also, any of the speakers from yesterday or today, if you have further questions for them, please feel free to get in touch with them based on their contact information provided on the list of attendees. So with that being said, we will sign off for today, and we will see you all back here again tomorrow morning at 9 a.m. Thank you.